In this video, you're gonna understand probability distributions, the normal distribution, the binomial distribution, the Poisson distribution, and the t-distribution. You ever notice how some things in life kind of seem random, but in reality there's some sort of pattern to them? We're gonna talk about all of that today. My name is João Evangelista, I'm a fourth-year medical student, and this is the Meta-Analysis Academy, where we teach the science of systematic reviews and meta-analysis to thousands of students in dozens of countries all over the world. Let us begin. What is a probability distribution? Think of probability distribution as a kind of map of possibilities. We have several outcomes, and it tells us how likely each of those outcomes is to occur in the real world. If you could possibly gather all data regarding a population and you graphed it would be in a probability distribution. Like if you gather height of 1,000 women, by definition, half those women will be above the average and the other half would be below the average. Seems easy, no? But what about if I calculated, okay, what's the average height of a woman in the 75th percentile, which would mean she's taller than 3 out of every 4 women in that distribution. That's a bit trickier, huh? But that is the essence of probability distribution. So let's talk about these probability distributions. One of them is the Gaussian distribution, what's called the normal distribution. This is what a normal distribution looks like. Height, like the example that I gave you, like the height of 1,000 women, would be distributed normally. IQ is distributed normally, blood pressure is distributed normally, which means basically that most people are kind of close to the average. Approximately 68% of everyone is within one standard deviation of the average. If we're talking about height, within one standard deviation of the average, we would have 34.1% of people being more than the average height, and then 34.1% of people being less than the average height, but still very close to the average itself. This is actually one of the statistics questions that shows up the most during USMLE Steps 1 and 2 CK exams. Because this thing about standard deviation, normal distribution, 68% closer to the one standard deviation mark or whatever, this is actually such a fundamental concept of statistics that people want you to know this even as a basic medical knowledge. If we were thinking, for instance, about male height, and we already know that male height is normally distributed, which means it follows a Gaussian distribution, but then we have like more than 3 standard deviations of height, which means those people are in the 0.1% of tallest people. That's when you get like NBA basketball players or whatever, like people of extreme height, more than 7 foot tall. But looking to the other end, you also have people who are equally far from the average, but to the other side. People who are on the 0.1% of lowest heights for people, potentially people with dwarfism or some other medical conditions. All right, normal distribution is understood. Now let's talk about binomial distribution. The binomial distribution describes situations in which you have 2 possible outcomes for a given number of events. I'm gonna explain what I mean right now. Let's say that you only have like 2 possible outcomes, yes or no, failed or approved, heads or tails. Now let's say that I flip this coin 10 times. What are the odds that I'll get 7 heads? The chance of that happening follows a binomial distribution. And it can give me what's the chance of me getting 0 heads, 1 head, 10 heads. Something else that we need to talk about is the Poisson distribution. God, I hope I'm pronouncing this correctly. The Poisson distribution. The Poisson distribution is for rare events in time. Like, let's say, how many DNA mutations happen over the course of a day in a single DNA strip. It's like a counter for events that rarely occur, relatively rarely, but even though they're rare, we kind of know how constantly we're going to get them. And that's that constant that you see in the equation. The Poisson distribution is not just interesting. It is the most statistically correct way to distribute things over time. When we pool the data for statistical analysis, and we're talking about adverse events or number of times an epidemic occurred over the last, let's say, 100 years, any outcome that we can measure over a specific period of time can be like distributed in a Poisson distribution. We call this regression, and it is very important for a lot of researchers. The last distribution that we need to talk about is the t-distribution. The t-distribution looks a lot like a normal distribution. However, as you can see, the extremes are fatter. We're going to use the t-distribution instead of the normal Gaussian distribution when we're talking about a population that is very small, or when we don't know the standard deviation from that particular data set. In other words, when we are less certain about our estimations, the t-distribution is the foundation for real-life statistical inferences, confidence intervals, and t-tests. This is very applicable in real-world research, especially when the sample size is not huge. And I'm going to give you a simple example that will help you grasp this concept. Let's say that you're developing a blood pressure medication specifically for a very rare disease. You could only really find 10 patients with that rare disease that would be able to join your trial. Let's say that you took the average of reduction of systolic blood pressure and you got 5 millimeters of mercury. That is extremely relevant. It's good information to know, but if we're being honest, this is not a lot of data to go on. It's better than zero, but it's not a lot. What the t-distribution does instead of the normal distribution is that it is cautious about those inferences on real-world other people who also have the disease. Review of the topics. Each distribution, normal, binomial, Poisson, t-distribution, they all give different certainty maps. Even better is to say that they give uncertainty maps. When we calculate confidence intervals, p-values, even regression, we're using these uncertainty distributions to understand the data that we're collecting, that we're managing to calculate using statistics. That allows us to make better estimations of how those results are going to behave in the real world. That's why, for instance, we need that the confidence interval doesn't cross the null value. And this concept of uncertainty distribution is extremely important. If I distribute my results in an uncertain way, but still all the confidence interval that I distributed, that I calculated, doesn't cross the null value, then my result is statistically significant. It's absolutely applicable by people in those kinds of conditions, by the population that I was studying. So what I can say is I have uncertainty about where the data lies really inside this confidence interval, but because the confidence interval doesn't cross the null value, then my result is statistically significant. It is mathematically relevant. It's proved. There's no price on data like that. It's very important. I hope you now understand probability distributions, and even more than that, why this is so crucial for meta-analysis, for research in general, etc. Don't forget to check our up-and-coming videos. We always have good stuff coming out all the time. Explanation videos like this one, Metacast episodes with successful people in their own fields, publication roadmap live streams, and many more good videos in future. That's it from us. Bye-bye.